So today we'll start off with acids and bases, and today is kind of an easy day, and I'm not being sarcastic when I say that, because my hope, my goal, is that this is not the first time you've ever talked about acids and bases, and I'd be very, very surprised if this is the first time. So acids, for the most part, when we talk about acids and bases, there's an easy way to detect whether you're looking at an acid or a base. And I think I may have said this earlier in the year, before Christmas, when we were writing out formulas. Remember when we had to write names and all that fun stuff? Oh, the good old days. How in the world can you tell that hydrochloric acid, if you didn't know the name of it, or HCl, was an acid? H is in the front. H is in the front. Very good. So if we have a hydrogen up front, you're looking at an acid. And other than seeing hydroxide in the back, how do you know that's a base? Other than skip the OH, because not all bases have OH, which is kind of wacky. So if you can tell that it's an acid with a hydrogen in the front, you can tell it's a base because there's a hydrogen in the back. So if it ends with a hydrogen, you're looking at a base. If it starts with a hydrogen, you're looking at an acid. So riddle me this. What if you have a hydrogen on the front and the back? It's either. So this is a cool little term. It's called amphoteric. Amphoteric simply means that this substance can act as either an acid or a base. Okay. So there are a lot of those things. Water is not the only one, but it does have both a hydrogen in the front and in the back. And when you write water correctly, this is how you write it. This is garbage. We don't like water like that. There's two types. There are two different types of acid and base theories that we will talk about. There's truly three, but we don't talk about the third one. But before we talk about those types, let's talk a little bit about some characteristics about acids and bases. All acids and bases that we will be dealing with are ionic in nature, which means that the hydrogen ion breaks off, which acts like a metal in this case, and causes the solution to become more acidic. Or, in some cases, an hydroxide will break off and will make it more basic. So, all acids conduct electricity. I'm not going to have you do a tasting contest in here, which one's more sour, sulfuric acid or hydrochloric acid, but they do taste sour. You know that because of some of the things that you have eaten that are, quote unquote, good for you to eat, not chugging hydrochloric acid. Also, acids react with active metals to produce hydrogen gas, and they do this really well and explode. They also neutralize bases, which we'll talk more about on Wednesday with neutralizations. And we don't use litmus paper in here. That's mainly for like junior high and middle school, all those fun things. We use pH probes in here. We'll have a lab after the test because my student teacher only has 2 weeks left. So we'll do that afterward. Some common examples of acids: citric acid, acetic acid. Acetic acid is known as vinegar, so we use vinegar quite a bit. And then some that we don't want to ingest. Bases also conduct electricity, and they taste bitter. Bases feel slippery when wet. Okay. Soap. They neutralize acids. Also, they change litmus paper blue. Some common examples: sodium hydroxide, potassium hydroxide, and probably ammonia. If you have a cat, you know. So here are the two acid and base theories, and these will be similar to your homework. So the theory I want to talk about is called Arrhenius acids and bases. And these are the type that hopefully you have learned about back in the day. Anything that produces hydrogen when it dissociates is considered an acid. Okay? Anything that when it dissociates produces a hydrogen is considered an Arrhenius acid. If it produces hydroxide when it dissociates, then it's safe to say that it is an Arrhenius. Please tell me that you've seen that before.
I've seen it, but that doesn't mean I haven't seen it.
Yes. Now, here is something that somebody asked about in first hour. They go, well, what about ammonia, NH3? How does it behave as an acid or base? Well, it doesn't dissociate into anything that we would recognize as either hydrogen or hydroxide. But what ammonia does to water, ammonia actually rips a hydrogen off. So if it takes that hydrogen away, what remains? Hydroxide. So that is not considered an Arrhenius base because it does not, A, dissociate, and this is actually segueing into our next type of theory, which is Bronsted-Lowery acid. That is the next theory. So that would not be an Arrhenius base because there was no dissociation of that, number one. But there's only two of them. Which is, yeah, we won't do Lewis acids and bases. That's,
why are they facts? Why are they just theories? We just did prove it.
all right, Bronsted-Lowery. This is a proton or hydrogen ion donor is considered an acid. A hydrogen ion acceptor is considered a base. I'm going to do some examples here. So if you donate hydrogen ions, you're an acid. In other words, you break it off and say, here, this is for you. You're an acid. And if you're like, I need that, and take it, then you're considered a base. Yes? Uh-huh.
You could say that HOH or water donated this with the acid, but NH3 would be a base, right?
That's exactly where we're going. Perfect. All right. Here's an example of a situation that you would be asked. And we'll do some more practice problems. This is just an example here. But when you look at this, you want to look at the before and after situation. So here I have NH3. And how many hydrogens does NH3 have? 3. And then when we look on the other side of the arrow, this NH3 either gained a hydrogen ion or lost a hydrogen ion. We gained it, yeah, because now it went from 3 to 4. Looking at water, which is written incorrectly, but it's okay. How many hydrogens does water have? How many does it now have? 1. So here's what happened. The water actually donated a hydrogen ion to the ammonia. Because it donated a hydrogen ion, the water is considered an acid and the ammonia is considered a base. If I were to flip this arrow around, which we're going to start to trek into, we can do that. If I want to get NH4 with a +1 charge back to NH3 with no charge, how would that happen? It would donate a hydrogen. So here on this side, it's acting like an acid, but we can't say that it's an acid because acids and bases are only on the reactant side or the left side. Okay? So if we have something that's on the product side, then we call it a conjugate acid. So it still behaves like an acid, but it's on the product side. So here we have a conjugate acid, and then the hydroxide would be considered a conjugate base. Conjugates are always on the product side. Acids and bases are always on the reactant side. Okay? Let's do another. And then we'll do some practice problems. All right, so here, again, looking at HCl and water, which is written incorrectly. Okay, so the hydrochloric acid did what? Donated a hydrogen. Very good. And it went from HCl to just chlorochlorine. And then the water accepted that hydrogen, so it now has three hydrogens instead of 2. Now, also, are you keeping track of the charges? So if I donate a +1 charge, what should happen to the charge of this? You should get more negative, right? So if I give away a positive charge, I'm going to become more negative. If I accept a positive charge, then I'm going to become more positive. And did that happen? Okay. You could do that. So here it goes from 0 to a negative charge. And then here it started off 0 and went to a positive charge. That's another way of doing it. More negative. Yeah, acids will become more negative as it becomes a product, and the bases will become more positive as it becomes a product. Cool. Bases accept, so they become more positive. Or I'm sorry. No. So here it becomes more positive. And I said that, yeah. All right. So here is a practice problem here. 2 of them. Now here is a typical type of question I may ask on a test. So you're given an equation, and I'll give you like 4 options, multiple choice. And this one's saying, who's the conjugate base? Okay. Now, if you have 4 options, 2 of those options are gone. Which 2 options could be removed? Yeah, so these guys here. So keep that in mind, and especially whenever you're looking at multiple choice, eliminate anything that doesn't make any sense. All right, so let's take a look at this. So H3O plus goes to H2, so what has happened? Lost a hydrogen, which means it donated a hydrogen. Now, you may want to write that arrow with a hydrogen. I'm not requiring you to do that, but it probably will keep you from doing something dumb. Okay? Just saying. So in this case, H3O plus is an acid where the water is acting as a base. If I switch the arrow and I want to go back the other way, what's going to happen? Because for the H3O plus, it has to donate a hydrogen since there's 3 there and there's only 2 here. So H2PO4 would be the conjugate base. So that would have answered our question, where this is our conjugate acid.
I thought bases. Oh, no, I thought bases were positive.
No, bases
Okay.
accept, so they
Bases become more positive. So here it has no charge. Then it becomes positive because of the acceptance of the hydrogen. Okay. On the other side, okay, the base is going to become more positive as it goes from here to here. So -1 to no charge is becoming more positive. Now, keep in mind that conjugate simply means that we are looking at the product side. Poor guy. Let's look at the next example. Okay, you look flustered. Try this next one on your own. Don't peek up here. Abby, I'm picking on you, so get ready. I'm picking on you. I'm not doing anything. I'm letting Abby tell me.
I already finished.
You're not Abby, are you? You're just identifying. Yeah, everything. All right, Abby, what do you got? So NH3, what's it doing? Is it gaining or losing a hydrogen from here to here? Okay, right here, NH3, is it gaining or losing a hydrogen as it goes from a reactant to a product? How do you know that? What's that? What does? Okay, so how many hydrogens do we have here? How many here? That tells us that it's gaining. Okay. So NH3 is acting as what? Acid or base? Acid or base? Base. Very good. So again, if it accepts a hydrogen, it's a base. Water in this case is acting like an acid. What was water up here? A base. That's an amphoteric substance. Nice. Okay. And then for the NH4 to go back to NH3, Celeste, what's it need to do? Good. Very nice. So this is a conjugate acid and this is a conjugate base if we were going in the opposite direction. Very nice. Okay. Chemistry. Everybody good? Seem easy? You'll see very difficult type questions like this on Monday.
Yes.
And the test. Don't forget about the test. All right, so part of the homework, not all of the homework, part of the homework is this worksheet. Okay. You have it. I promise. It's called worksheet number 1, Bronsted, Lowery.
See, look at this.
Right there. If you don't, copy it over from the content library. Don't delete it. But that's not all. We got more. Let's go back.
What?
Yes, there's more.
You can get one each box done in 9 minutes.
And the 2s, yes. Yes, yes.
Are the twos just the same thing as the ones?
Ah, no, 2s are much more fun. All right, so let's look at this practice problem. Okay, everybody listen? All right, so the first practice problem that kind of leads us into the 2s says the following substances act like Bronsted-Lowery acids. Shh. Ethan, thank you. The following substance act as a Bronsted-Lowery acid. Okay. Reading the question is going to help you answer the question. I don't know. Okay. And it's in water, so that means that you're reacting it with water. So it wants you to write the chemical equation and it illustrates this reaction with water. So if HCO3 with a -1 charge or bicarbonate acts like an acid, what will I have on the product side? What's that? Water's acting like a base. If this is acting like an acid, that's good. So that's a good heads up. And how do you know that's acting like an acid? Because it says so right there. Good. Okay. True, true. So it's donating a hydrogen, which again I would illustrate. And what will my products be? Okay, hold on. CO3. So if it had a -1 charge and it lost a plus charge, -2. And again, if you forget that, -1 minus a +1 equals -2. And CO3 is one of our 10 polys. So make sure you still remember the polys and the charges. And what else is produced here? H3O, hydronium, with a +1 charge. Hydronium. And if you were to label these, what would CO3 with the negative charge or -2 charge be called? Conjugate acid, conjugate base, conjugate base. Because if we were going in the opposite direction, that would need to happen. Okay. Now, the question doesn't ask you to identify the acid base, conjugate acid. That's probably good practice, just to make sure. The only thing that you were given was that right there. That information. Okay. Let's do the next practice problem. Okay, everybody good there? Is this material difficult?
Yes.
All right, number 4 says the following substance acts as a Bronsted-Lowery base in water. Now, wait a minute. Isn't that the same thing that we just had as an acid? What? It's amphoteric. There we go. Nice. Okay. So in this case, it's still reacting with water. And so in this case, it's doing what? It's accepting a hydrogen Remember, bases accept a hydrogen. So on the product side, what do we have? H2CO3, and what's the charge on that? No charge. Very good. So -1 plus 1, 0. Okay. Anybody remember what H2CO3 is called? No, it's some kind of acid. Carbonic acid. Very good. Okay, so carbonic acid. Let's make that look a little cuter. But when you learn something, you don't forget it. And what's the other thing that's produced here? Hydroxide. Okay. Now, make sure that the charges are the same on both sides. So -1 plus 0 equals -1. 0 plus a -1 equals -1. So that's a good way to check that. Also, if you just are doing this for kicks and giggles here, we got base, acid. What's this called? Conjugate acid, conjugate base, because it would give away a hydrogen ion. What's that? The only thing that was asked is for you to produce or write the equation. Yeah. Everything that's right here is what I'm looking for. Everything else is to help you get where you need to go. All right, so the 2's are also part of your homework. So worksheet number 1 and the 2's.